Hello everyone, and thank you for joining in. My name is Clara, and I'm currently a project scientist at the University Corporation for Atmospheric Research, or UCAR, in Boulder, Colorado. Today, I'm going to be talking about how we can use ground-reflected GPS signals to monitor the terrestrial hydrologic cycle. Given that this workshop is aimed at geodesists and seismologists, I thought I'd start with a little background on just what the terrestrial hydrologic cycle is and why we're interested in learning more about it. I'm pretty confident that most of you are actually already familiar with the terrestrial hydrologic cycle, even if you don't even realize it. If I had to guess, I would say that all of you probably know that dirt gets muddy when it rains, plants need water to live, and that snow is frozen water. Those of us who live in the western US are increasingly aware that the absence of rain creates drought, which creates dry vegetation, which then can lead to wildfire. And a lot of you probably know that many states like Colorado and California rely heavily on having a solid winter snowpack in order to have enough water for the following summer. The amount of snow on the ground, the amount of water contained within the vegetation, and the amount of moisture in the soil are all components of the terrestrial hydrologic cycle. Terrestrial hydrologists quantify the amount of water contained within the land surface and study how and when water moves between the different components of the hydrologic cycle. Doing this is important because we want to be able to quantify and understand how drought evolves, be able to forecast possible flooding, we want to predict how bad a fire season might be, and estimate how much water we'll be able to use in the future. So how does one quantify the amount of water contained within anything? How would I figure out the water content of this tomato, for example? Well, I could weigh the tomato, then dry it out, and then weigh it again, and then the difference between the two weights would tell me how much water was in the tomato. But doing this isn't awesome because now you don't have a tomato anymore, so who cares how much water was in it? Though this is actually something that people do to figure out how much water is in either vegetation or soil, and this is one of the only direct ways to measure the water content of a thing. But increasingly, scientists and engineers are turning to indirect ways to measure water content, where you don't actually have to destroy the thing to know how much water was in it. There are a couple of different ways of indirectly measuring the water content of soil or vegetation, though today I think I only have time to talk about one of them. And I think you will all actually be familiar with this too, now that I think about it. I think most of us have probably cooked food in a microwave before, right? Your microwave oven works because water is really excited by microwaves. Microwaves cause the water in your food to jiggle around, and all that jiggling creates heat, which cooks your food. Though I'm betting most of you knew that already. But microwaves are also extensively used to remotely sense components of the terrestrial hydrologic cycle. Let's pretend that we have a radar that's transmitting microwaves towards something. Let's say some bare soil. The microwaves are going to interact with that soil, with part of the incoming energy being absorbed by the soil, some of it being transmitted through the soil, and then some of it being reflected off of the soil. The extent to which the microwaves are absorbed, transmitted, or reflected depends on the dielectric constant of the soil, as well as the angle of the incoming transmission. The higher the dielectric constant of a medium, the more reflection you're going to get. And as it turns out, the dielectric constant of most natural materials like soil or vegetation is mostly dependent on its water content, with wetter soils or vegetation with a lot of water having higher dielectric constants and vice versa. So if you can measure the dielectric constant of the ground by bouncing microwaves off of it, you can get an idea of how much water is in it without actually having to dry it out first. And this principle has long been used by several different types of sensors, from small probes to satellites, to measure the moisture content of both soil and vegetation. It just so happens that Global Positioning System, or GPS satellites, also transmit microwave signals. And the 32 satellites that comprise the GPS constellation are constantly bathing the Earth in microwave radiation so that your cell phones can direct you to the nearest coffee shop, or so that we can precisely measure the movement of Earth's tectonic plates. There are a lot of researchers who actually use these GPS signals to remotely sense the terrestrial hydrologic cycle. And this field of research is commonly called GPS interferometric reflectometry, or GPSIR for short. Some researchers have also examined how navigation signals from satellite constellations other than GPS can be used for remote sensing, and in that case, the umbrella term is Global Navigation Satellite System Interferometric Reflectometry, or GNSS-IR for short. But I personally only have experience with GPSIR, So that's all I'm going to talk about today. Though from what I've read, GNSS IR is just a different flavor for the same basic thing. One thing you need for GPS IR is a GPS antenna and receiver, ideally not too far off of the ground, maybe just a few meters. Here I've drawn a pretty terrible cartoon of a typical GPS antenna that you might find as part of the Plate Boundary Observatory, or PBO network. Here's a real picture of a PBO antenna. These antennas are typically about 2 meters tall. They have these cylindrical legs that go really far into the ground in order to be anchored to bedrock, and on top of these legs is that half spherical thing, which is called a radome. A radome is just a cover to protect the GPS antenna from the elements. Here's a picture of what's under the radome, the GPS antenna itself. The PBO network is comprised of hundreds of GPS antennas that are mostly positioned in the western United States and Alaska, and the purpose of these antennas and receivers is to measure the movement of tectonic plates. What GPS IR does is repurpose GPS antennas like the PBO antennas to not only measure tectonic plate movement, but also remotely sense the hydrologic cycle. And you can utilize this technique with many different kinds of GPS antennas, not just PBO antennas, but these are the ones that I have experience using. What a GPS antenna does is it intercepts transmitted signals coming from the 32 GPS satellites, which are transmitting L-band microwave signals that tend to be either 19 or 24 centimeters long, and these signals are transmitted at all hours of the day. GPS receivers record a type of data called signal-to-noise ratio data, or SNR data. It's a measure of the strength of the received signal relative to the amount of noise in the data. And if we look at how signal-to-noise ratio data changes as one particular GPS satellite rises and then sets in the sky, then we will probably see something like this, where our SNR data is relatively low when the GPS satellite is close to the horizon, and then as the satellite rises overhead, SNR increases, and then it decreases again as the satellite sets. Note the wiggles at the low elevation angles. What are they caused from? In order to explain the wiggles, let's make a vast simplification about the incoming GPS signal. So each GPS satellite sends out these L-band microwave signals, and these signals also look like wiggles. The signal that the GPS antenna wants to receive is called the direct signal, and this is the signal that travels directly from the GPS satellite to the antenna. This is a signal that ultimately helps the GPS receiver determine its position, which is what it was designed for. However, part of the GPS signal doesn't travel directly between the satellite and the antenna. Part of it will first bounce or reflect off of nearby surfaces before it hits the antenna. Here I've represented the direct and reflected signal as two different wiggles or sine waves, or whatever you want to call them. These reflected or multipath signals are usually considered to be a source of noise in GPS data, and engineers try to design antennas that suppress the reflected signal as much as possible. But for those of us interested in GPS IR, we like that reflected signal. One important thing to see here is that the direct signal actually arrives at the GPS antenna first, and the reflected signal comes in afterwards because the reflected signal has to travel a greater distance. The end result of this is that the direct and reflected signals are going to arrive either in or out of phase with one another, depending on the elevation angle of the GPS satellite. And if you remember from maybe high school physics or some other math class, that when you add two waves that are completely in phase with one another, that the end result is an amplified wave. And if you add two waves that are completely out of phase with one another, that the waves will cancel each other out. And this is what's happening at those low elevation angles in the signal-to-noise ratio data. Those wiggles are the result of the interference between the direct and reflected signals. Now you may be asking why there are only these interferences at low elevation angles and not when the satellite is directly overhead. One major reason is the gain of the GPS antenna. It's much higher at zenith than it is off to the sides. In other words, these GPS antennas are designed to be really good at receiving signals that come from higher elevation angles and not so good at receiving signals from low elevation angles. So the interference between the direct and reflected signal will produce the wiggles we see in the SNR data. But what if the reflected surface changes? Remember how I said earlier that bouncing microwaves off of the ground can help us infer the dielectric constant of the surface, which itself is a function of how much water is in the soil or on the surface or in the vegetation? The reflected GPS signal will also change if the dielectric constant changes. So how will the reflected GPS signal change if it rains, which means the soil moisture will increase? What about if vegetation near the GPS antenna grows? Or how about if it snows? These are the scenarios that I'm going to talk about today. After this talk, hopefully you'll understand a little better how we can use GPS signals to infer changes in soil moisture, vegetation parameters, parameters and snow depth in the vicinity of a GPS antenna. And when I say the word vicinity, you're probably wondering what that means. When we use GPS IR to measure snow depth, for example, over what area are we measuring it? Is it a point observation? Does it give snow depth data for many square meters, square kilometers? The answer to that question is, it depends. The spatial footprint of the reflected signal actually changes as the GPS satellite rises and sets in the sky, with larger spatial footprints at smaller elevation angles and vice versa, and taller GPS antennas will have larger footprints. But for the 2-meter tall antennas of the PBO network, we average several footprints from several GPS satellites each day. We can estimate the average daily footprint being around 1,000 meters squared. Let's go back to the conceptual time series of signal-to-noise ratio data that I showed earlier. This time series, which I'm showing as a function of the satellite elevation angle, is a combination of both the direct signal and the interference between the direct and reflected signals. The direct signal component can be approximated as what I have drawn in the middle panel, kind of a parabolic arc. It's going to make things a lot simpler if we remove the direct signal from our signal-to-noise ratio data, and if we subtract it out, we're left with what I've shown in the bottom panel, just the interference between the direct and reflected signals. That middle part of the interferogram is kind of boring and doesn't contain any useful information, so we'll just focus on the wiggles here, from when the GPS satellite is rising in the sky. So you could also use the data at the end of the interferogram, when the GPS satellite is setting, if you wanted. So for the remainder of the talk, this is the only thing we're interested in. This is what those SNR wiggles look like in real life. This is an SNR interferogram recorded from one of the PBO antennas. So how do these interferograms change when soil moisture, vegetation, or snow depth changes? Just looking at SNR interferograms themselves and how they change over time is hard. For example, here are 2 interferograms from the same GPS antenna that were recorded before and after a rain event. They're a little different, but it's not super obvious how they're different, and the noise in the interferograms seems to get in the way. So what GPS IR does is simplify the interferograms with the following equation. This is the equation for a sine curve as a function of elevation angle with amplitude A, a frequency term, and a phase offset. What you can do is fit this sine curve to each interferogram to estimate these parameters, and then look at changes in the parameters themselves with time. Let's take a look at these parameters, or SNR metrics, as we used to call them. Most of you probably know what amplitude is. It's just how tall the wiggles are. Notice that in our real data, amplitude appears to vary as a function of elevation angle, with larger amplitudes at lower elevation angles. But our SNR equation just basically estimates an average amplitude for each SNR interferogram, and for our purposes that's largely fine. Then we multiply our amplitude by a cosine term, and within that cosine term we have a frequency term plus a phase offset. The phase offset is relatively straightforward. It just describes how the SNR interferogram shifts back and forth. The frequency term is more complicated. In the past, it's been modeled as the sine of the elevation angle of the GPS satellite multiplied by 4 pi times this thing that we call the effective reflector height. And then we divide that by the wavelength of the GPS signal. Effective reflector height seems like a weird term, but what we're talking about is a calculation of the distance between the reflecting surface, or the ground, and then the phase center of the antenna. You can't actually measure this distance physically, but you can estimate it when you fit the SNR equation to your observed data. This means that the frequency of the SNR oscillations is a function of the effective reflector height of the antenna, with taller antennas producing higher frequency oscillations, and vice versa. This is the key concept behind using GPS IR to measure snow depth surrounding an antenna. As the snowpack grows, the height of the antenna relative to the snow surface actually gets shorter, which is going to produce a change in the frequency of the SNR oscillations. So if you see a significant change in the SNR frequency, and you know your GPS antenna isn't sinking into quicksand, you can infer that it has snowed, and actually use the change in effective reflector height as a proxy for a change in snow depth. That's all I'm going to say about this today, because snow sensing using GPS IR is not exactly my area of expertise, but here are a few papers you could check out if you're interested. Something that at one point in time was my area of expertise, though, was using GPS IR to retrieve soil moisture near a GPS antenna. And that's what I would like to focus on now. So let's look at these 2 SNR interferograms. One was recorded before a rain event, and one was recorded after a rain event, where the soil moisture was way higher than it was before the rain came. And what we're going to do is fit our characteristic SNR equation to both of them. The fitted curves are shown here, where the gray curve is estimated using the observed data from before the rainstorm, and the green curve is estimated using the observed data from after the rainstorm. Now it's a little easier to see that the increase in soil moisture from the rain caused a slight decrease in amplitude and a small phase offset as well. We can make a time series of the phase offset, which is going to be different each day, and compare it to a time series of soil moisture that was measured at the same GPS antenna where the SNR data were recorded. The figure at the top shows soil moisture as a function of time, and we can see that around day of year 253, soil moisture increased a lot really quickly, followed by a slow decrease in soil moisture that starts around day of year 260. The bottom plot is a corresponding time series of phase estimated from SNR data for the same location. On the same day as the big increase in soil moisture, we see a big increase in phase. And we also see that phase slowly begins to decrease around the same time that soil moisture started to decrease. So empirically, we can see that there appears to be a pretty good correlation between phase and soil moisture. And if we see an increase in the phase of the SNR data with time, then we can assume that there has also been an increase in soil moisture in the vicinity of the GPS antenna. What if you have vegetation growing around your antenna? How would you expect SNR data to change in that case? Well, here's one example of how grass growing around a test antenna in Oklahoma changed the SNR interferogram. The SNR data on the left were recorded when there was basically no grass growing, and the SNR data on the right were recorded in the middle of the summer when the grass was really high. There's a pretty obvious change in amplitude, with more vegetation corresponding to a smaller amplitude. So empirically, we can say that phase is going to increase when soil moisture increases, and amplitude is going to decrease when vegetation increases. Does this mean that we can just directly back out soil moisture by looking only at phase data and back out vegetation information by looking only at amplitude data? Not exactly. Remember those two SNR curves I showed earlier, before and after a rain event? We saw that an increase in soil moisture will also cause a decrease in amplitude. So it appears that a decrease in amplitude could mean that either soil moisture increased or it could mean that vegetation increased. And then there's another problem. An increase in soil moisture will often cause vegetation to grow. So if you're only looking at empirical observations of SNR phase, amplitude, soil moisture, and vegetation parameters, it's going to be really confusing to understand just what is affecting what and to what extent. Because of this, we tried modeling SNR data and how it should theoretically respond to both changes in soil moisture and vegetation parameters, like vegetation height and water content. This was a numerical modeling experiment that adapted a model for bare soil to simulate SNR data, and one of my projects was to add a layer of vegetation to the model. I don't have time today to explain the ins and outs of the model, but if you're curious, this is the paper that explains it. What we did was run a variety of simulations for various soil moisture and vegetation parameters, and first we looked at whether or not our simulations were able to match what we were actually observing in the field. And this is what we found. On the left, we have an observed SNR interferogram in black from a field site where we were monitoring both the soil moisture and the vegetation growth near the antenna. The blue line is what we modeled given the observed soil moisture value during a time when there was no vegetation on the ground. And we see that overall they match pretty well. On the right, I'm showing another observed SNR interferogram in black, but this time from a day when the vegetation at the site had about 2.5 kilograms per meter squared of water in it. What I want you to focus on is the blue line, which is what we modeled when we input the specific vegetation and soil moisture parameters on that day. And again, we see a good match, even recreating the temporary decrease and then increase in amplitude oscillations as we increase elevation angle. We then calculated the SNR metrics for these model simulations and saw how they changed for different soil moisture and vegetation parameters. And we again validated the model, this time using soil moisture and vegetation data from a GPS antenna located in an alfalfa field. The top panel of this figure shows a time series of the wet weight of vegetation, the height of the vegetation canopy, and soil moisture for the site. The middle and bottom panels show time series of observed phase and amplitude data in the open black circles, and the blue dots show what we simulated on the days when we collected vegetation and soil moisture information for the model. This helped us validate our model, as we saw a good match between observed phase and amplitude and modeled phase and amplitude. After we determined that we had a model that was able to recreate what we saw observationally, we used the model to come up with a retrieval algorithm, in this case specifically for retrieving soil moisture in the vicinity of each PBO antenna. If you'd like to read more about the algorithm and learn about the validation of the retrievals themselves, then these are some papers you should check out. We were able to apply our soil moisture retrieval algorithm to SNR data from dozens of PBO antennas throughout the western US, which effectively created a new soil moisture network. Soil moisture, vegetation, and snow depth retrievals coming from the PBO antennas were deemed the PBO H2O network. And although this project technically ended a few years ago, there remains significant interest in repurposing other GPS antennas or even designing really low-cost GPS antennas to do similar work in other parts of the world. So those are the basics of GPS IR and how GPS is helping us understand the terrestrial hydrologic cycle. If any of you have any questions, I'm always happy to try to answer them, so feel free to reach out. And with that, I'll let you get on with your day. Thanks!